For this example, we are looking at for the third degree Taylor series. So in other words, a degree 3 polynomial for sine of x expanded about c equals pi over 6. This means this expanded about the center is just telling us that it is centered at pi over 6. Okay, so, and I'm not going to work through every one on here. You can go ahead and fill this in yourself. One thing I want to point out is that when we write the polynomial, which is down here, when we write the degree 3 polynomial, this is not one, it usually because the center is not at 0, this happens, but this is not one where we have a really nice pattern for what the a sub n coefficients are. So this is not one that you're going to write as the sum of a sub n times x minus c to the other. Anyway, we're not going to be able to do this because there's no real clear pattern between these coefficients. If that's the case, then our answer just stops when we get to the third degree polynomial. Okay, so here's your third degree polynomial for this. Go through it on your own. Make sure that you are getting the same thing. Okay, then let's go through this one together. So here we're looking for the Maclaurin polynomials, and here we are going to do an nth term polynomial as well as the degree 6, or sorry, nth degree, degree 6 polynomial, and then we will use it to approximate cosine of 0.1. Maclaurin series means that we are centered at 0. So filling out my chart, 1, 2, 3, we need to go up to, okay, this says degree 6. I might not need to go to 6 here. Let's kind of see what happens with the pattern here. And then the nth derivative of x, and then the nth derivative at the center, which is 0 because it's a Maclaurin series. You can put a c there or a 0, doesn't matter. And then n factorial, which is 1, 1, 2, 6, 24. We'll see how far we need to go there. And then, let's see, x minus 0. I don't need to write that. I'm just going to write x to the nth. Okay, so it's going to be 1x, x squared, x cubed, x to the 4th. Okay, so my 0th derivative is cosine, cosine x. My first derivative, negative sine x. Second derivative, negative cosine x. Third derivative, sine x, cosine x, etc. I'll finish that in a minute if I need to. And then now I'm plugging in 0, so we do need to know some trig. Cosine of 0 is 1. Negative sine of 0 is still 0. Negative cosine of 0 is negative 1. Sine is 0. Cosine is positive 1, etc. And what I notice here is that if I have a 0 in this column, that term is going to be omitted from my polynomial. I don't need to write 0 divided by 1 times x or 0 divided by 6 times x cubed. If I have zeros in there, that's fine, and I'm just going to have powers of 0 to 4, and so I guess I need to go to 6. So we'll go ahead and finish these. So negative sine x, which is 0, so that one's not going to matter either, and then negative cosine x, which puts us back at negative 1. And this is 6 factorial. If you want to write 720, that's fine, or just 6 factorial. And that's x to the 6th. Okay, so then p sub 6 of x is going to be 1 divided by 1 times 1. Okay, and then minus 1/2 times x squared plus 1 over 24. And if you want to write this as 4 factorial to help us look for a pattern, that's fine. If you want to write 24, that's fine too. And then x to the 4th, and then minus 1 over 6 factorial x to the 6th. Okay, and then we can just stop here. We don't need to expand those, that's fine. Then we're going to use, I'll go back and do p sub n in a second, but we're going to use this to evaluate or to approximate cosine of 0.1. So then to evaluate cosine of 0.1, I know that that is approximately p sub 6 of 0.1. So I'm plugging 0.1 into this polynomial. So 1 minus 1/2 times, if I'm doing this by hand, then I'm going to go ahead and write it out as that's 1/10. So then we have 1 over 10 squared, and then plus 1 over 24 times 1 over 10 to the 4th, and then minus 1 over 720 times 1 over 10 to the 6. Okay, I'm not going to expand that by hand. And I will tell you that it comes out to be, where is it? About 0.995. Okay, let's check, does this seem reasonable? Well, I know that cosine of 0 is 1. So yes, it does seem reasonable that cosine of 0.1, something very close to that, is very close to 1. So looks good to me. Okay, now P sub n is the generic term. So that's really what we're looking here. So if I could write a generic term for this, okay, if I could write a generic term for this, then I would be looking for a pattern. Let's use this notation down here, this expansion, to try and look for a pattern. So on my first term, I have x to the 0, and then I have x squared, and then I have x to the 4th, and then I have x to the 6th. So if I want to write an nth term, let's do it this way. I know I'm going to have, this is alternating, so I'm going to have -1 to some power. I'll fill that in a second. And then I have some coefficient, and then x to the 2nth. Why am I doing 2nth? Well, if this is the 0th term, and then the first term, and then the second term, and then the third term, the nth term is going to have a 2n as an exponent on my x. Okay? So I don't want to do x to the nth and worry about the all these in between terms being 0. Okay? I'm just going to write the power here as 2n. Okay? Because I only have even powers. And then for my coefficient, so this is, I could think of this as like 1 divided by 1. This is 1 divided by 2, which happens to be the same as 2 factorial. Okay? And then 1 divided by 4 factorial, then 1 divided by 6 factorial. And so we see that we are dividing by 2n factorial. On the third term, we've divided by 6 factorial. On the second term, we've divided, not second, but like n equals 2. We've divided by 2 factorial, etc. Okay? And then last thing I want to check is, am I starting at a positive or a negative? For my 0th term, I have a positive, so we can write this as -1 to the nth. If I was starting with a negative term, that would be an n plus 1. Okay? So this right here is what I'm going to plug into my summation for the nth degree polynomial. Actually, let me not put it up here. Let me write it above. So let's say the nth degree polynomial is going to be the sum from, and we're starting at 0, of -1 to the nth over 2n factorial times x to the 2nth. Okay, there's my nth degree term. Now there is one more thing. It doesn't tell me to do this, but there is one more thing I want to look at here. We will have some questions that ask us, how do we use one Taylor series to obtain another? So let's say that we had another part to this question, and it said, how can we use, actually this is a Maclaurin series. Okay, so the Maclaurin series for cosine x to obtain sine x. Now, if I want a Maclaurin series for sine x, I could fill out a new chart and do that, and that would be fine. Okay, that would get me there. But if I already have the series for cosine x, I want to use that and the relationship between sine and cosine to write the Maclaurin series for sine, because I know that sine x is, so is equals, so sine x is an antiderivative for cosine x dx. Now this should look familiar because we did something like this in 9.7. Okay, so I know that I can replace this piece with this right here, the series notation, the sigma notation. Okay, so that's going to give me the integral of the sum from 0 to infinity of -1 to the nth over the quantity 2n factorial, make sure you have parentheses there, times x to the 2nth, okay? And then all of that times dx. Okay, And because 9.7 says we can integrate on a term-by-term basis, or we can integrate the nth term, then that gives us the sum from 0 to infinity of -1 to the nth over 2n factorial. And then now antiderivative of this part is going to be x to the 2n plus 1, and then divided by 2n plus 1, or times 1 over 2n plus 1. Move that over a little bit, okay? And then plus c. We do need to address the c situation, but also I'm going to combine these two things. If 2n factorial is 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 all the way down, then I'm multiplying that by 2n plus 1. So I'm just going to write that as 2n plus 1, the quantity factorial, okay? So I get the sum from 0 to infinity of -1 to the nth divided by the quantity 2n plus 1 factorial times x to the 2n plus 1. And then let's talk about c. Remember, to determine what c is, we evaluate this function, which is sine x, at some easy point, like the center. Okay, well, if I plug this is a Maclaurin series, so my center is 0. If I plug 0 in here, sine 0 is 0. And so if I set this equal to 0, I know that this part is going to be 0 plus 0 plus 0, because 0 to a power. And so c equals 0, since sine 0 equals 0. So I can ignore this, okay? So I end up with sine x being equal to the sum from 0 to infinity of -1 to the nth over 2n plus 1 factorial times x to the 2n plus 1. Okay, so this is an example of combining what we did with those two useful facts in 9.7 with what we did in 9.8, which is deriving the Taylor or Maclaurin series.